Let's do some problem solving. So I have this question for you. For the opamp circuit shown below, clearly mark, clearly mark and find the current in the feedback path. So first you have to identify the feedback path in here. This is actually a great test of your concepts because most of the students would likely mark this as the feedback. But remember, a feedback is between the output terminal and the inverting input. So this is the inverting input. This is the non-inverting input. So this is not the feedback resistor. This is the non-inverting input. This is the non-inverting input, and this is the output. So this resistor is serving as the feedback resistor. So we need to find the current. It can be marked upward, or it can be marked downward. Does not matter. So let us say this is the current, and let us mark it as I feedback IF. So we need to find this feedback current IF in this circuit. In this circuit, you can see this 20 volt, which is that, and the minus 20 volt. These are the two supplies that powers up this op-amp. When they are given, actually, we need to check whether the output voltage must be within this range. But for now, you can ignore this. But let me mark it that the output of an op-amp must always be between this range. We will study this later on when we study about saturation. When the op-amp saturates, its voltage cannot go beyond this 20 volt or lower than this minus 20 volts. So the output has to stay between this. And in this part, we say that the op-amp operates in its linear region. And that is where the linear circuit analysis applies. So let us solve this circuit and find this the value of this IF. So it does not matter where the in which direction the op amp is made. This pointed corner is always the output, and this marks the input side of the op amp. Okay, so again, let us start with what we know for sure. We know this is at 0 volt. This is at 0 volt. We know this is at 0 volt, and we know the current in this branch is 2 milliampere for sure. We know this for sure. We know the current in here is 10 milliamperes. This is 0 volt. This current is 10 milliampere. What we know for sure is again that there is no current flowing in here. We know for sure that there is no current flowing in here. We know there is no current going here, and there is no current going here. This is what we know for sure here. So if uh, this is 0 volts, let us say this voltage is V plus for this, because this node is the same as the non-inverting input V plus. Then we can apply KCL here, or NVA. We can write the NVA equation for this node V plus. So we can say V plus minus 0 over zero point 0.5, V plus with the plus in subscript, or the power exponent, V plus minus 0 over 0 0.5. We like to write the terms in the current terms in milliamperes. You see all the current sources are marked in milliampere, so be very careful about that. So this must be in K as well, so 0 0.5. And we know this current, invert current, is 10 milliampere, so minus 10, and then plus V plus minus 0 over 2 is equal to 0. We can, it's simple, one equation, one unknown, we can solve it to find V plus is equal to 1 over 0.5 is 2, 1 over 2 is 0.5, minus 10 goes to the other side, it's 10, and V plus is equal to 10 divided by 2.5, which is 4 volts. So we know this is at 4 volts. If this is at 4 volts, the ideal op-amp characteristics say this must be at 4 volt as well. This must be at 4 volt. This must be at 4 volt. And now if we can apply the node voltage for this node, we can write 4 minus 0 over 2, this current, outward current. This outward current is minus 2. This outward current is plus IF, equal to 0. So, and there is no current going from here to, so from this node there are 1 2 3 current carrying branches, and we have three terms here. So we can find 2 minus 2 plus IF says that IF is 0. So there is no current flowing in this 3 kilo ohm feedback resistor. If this is 4 volt and no current flows in this resistor, the voltage across this will be 0, and this would be at 4 volt as well. So if this is VO, we know, although this is not to be found, but I am just trying to tell you that look at the simplicity of op-amp questions. They are so simple to solve because of the ideal op-amp characteristics. So VO is 4 volt as well. We can easily find this current if we want to. It did not have any role because this is that load resistor, and we have seen up till now that load resistance does not play any role in determining the voltage across it. The rest of the circuit does this. So if suppose we want to find, the question says find this IO that goes into the op amp, what we will do, we will find this current. We know this current, we can apply KCL here. So this current IL would be VO minus 0 over RL, which is 4 over 8K, that is 0.5 milliamperes. And we know IF, so at this node, the KCL can be applied, minus IF plus IO plus IL is equal to 0. So we have IO equal to IF minus IL, and IF is 0 and IL is 0.5. So IO is minus 0.5 milliampere. Look at the simplicity of the op-amp problems. It's very simple to apply basic circuit analysis concepts, especially the node voltage. I have deliberately tried to refrain myself from applying KVL anywhere. It is because of several things, but you see that that use of KCL or the node voltage equation at various nodes is very easy, especially the input nodes is super simple.